Welcome everybody to our Twitch stream. For those of you who've not met me before, my name is Mike Freeman. I'm excited to introduce myself as a developer advocate here at Observable. I've only been on Observable's team for about a couple of weeks now. I think I'm the newest hire still. And it has just been a blast taking my background in creating educational materials and joining these folks making just such awesome software to allow folks to do it. We're going to have a super fun stream here today. We've got our guest, Matt Dzugan. Before we let him introduce himself, I'll turn to my co-host so Anjana can introduce herself.
Hi, folks. Anjana here, coming at you from San Francisco. Also developer advocate here at Observable. Really excited to be back on stream with y'all, and super excited that we have Observable ambassador and space data visualizer extraordinaire, Matt Dzugan, here with us. Welcome.
Yeah, thanks, guys. Super happy to be here. Yep, like you guys said, my name is Matt Dzugan. I'm a data scientist. I actually got started doing kind of data science-y modeling and simulation stuff while I was working in the space division of the Boeing company, doing kind of models and simulation stuff for satellites. So kind of been thinking about doing something with this data set, and yeah, really excited to kind of explore it here on this Twitch stream. Solar eclipses are really cool, and kind of want to visualize them. So one of the cool things about eclipses is there's kind of like a certain recipe to make them happen. So you can see this image here on my screen. This is a total solar eclipse. This is what I was trying to show, which I now know probably no one saw. So basically what this is you can see the moon blocking the sun. And so this is all due to the size of the moon, how it looks from Earth. It's less of, of course, the actual size of the moon matters, but what really matters is how big the moon looks from Earth and how big the sun looks from Earth, which is, of course, based on the actual size of the sun and size of the moon. But there's a couple more things at play. So what we want to do is kind of take a data visualization approach to exploring all those different variables and sort of understand like what eclipses would look like on the surfaces of different planets. So if you think about it, I was kind of trying to show this. So this is like the size of my phone. It's basically totally blocking the stream. You can think of that as like an eclipse, but as I move my phone further away, it doesn't totally block the stream. It blocks some part of it. And if I move my phone like super close, then it like, oh my gosh, definitely blocks everything. So it's the same thing with the moons. So different planets have different numbers of moons, and actually some planets, Mercury and Venus, have no moons. And of course, Earth, we just have one. So what's cool is you can take the size of those moons, explore how far they are away from the planet, then take the size of the sun, explore how far that is away from the planet, and you can sort of simulate what the eclipses would look like.
And so, let's be clear for a second here, Matt. You are only interested in the perfect eclipse. You don't really care if the moon is so much larger than the sun and totally blocking it out. You want that like swoosh moment when they align, and you can see that very cool backlit.
Exactly, because just like if I probably try to perfectly align my phone with the stream, like you can still see a little bit of light kind of oozing around it, whereas if I just totally block it, like you see nothing. So what's cool with the image that I'm sharing on my screen is you can sort of see, I guess, what's called now unfortunately named the corona of the sun is like kind of like bleeding across here. So we can kind of get that effect, whereas if our moon was, let's say, 10 times bigger, you wouldn't see that. It would just be a black sky. So one of the very first things we can do, and again, we're going to walk through exploring this data in a second, but I kind of just want to tease and build into this, is we can use actually these emojis to sort of explore the different sizes. And so Mike and I have been trading off different ideas for different ways to sort of visualize this data. And so one of the ideas that we had is to kind of create some visualizations that use these emojis. And so just here you can see, like when I'm on Saturn, for example, Saturn's got a lot of different moons. In fact, you guys probably all know Jupiter has like a ton of moons. But as you can see, their sizes as compared to the sun are much different. So on Jupiter, we couldn't get this like super perfect eclipse because these moons, in fact, are just like totally bigger than the sun. So you can sort of see here for these different planets. By the way, this notebook that I'm on is linked in the notebook that we added to the chat. Similar for Uranus, no jokes allowed, Neptune, and yeah, all the other kind of gas giants. So what's particularly cool also is that Jupiter has like many moons, I think like even hundreds, but what you can see on this viz is all the other ones are too small to even render. These 4 are the ones that were originally, what do you call it, discovered, I guess, by Galileo. They're called the Galilean moons. I think he literally just like hacked together a telescope in his like whatever era he was from the 1600s or whatever, and he managed to see these. So that's pretty cool. Anyway, I'm digressing a little bit. So Mike and I have kind of been trading ideas on how we can visualize this eclipse data. So one of the ideas was to kind of use these emojis. Another idea that I sort of had is to kind of like plot the data, plot the size. We'll sort of explain this in a little bit more later, but it's this kind of idea that you could plot the size of the sun, the size of the moon, and anytime they're the same size, which is along this red line, you get this kind of perfect eclipse that we were talking about. So,
and what is that blue small rectangle, Matt? What could it be?
The blue small, spoiler alert, the blue small rectangle is actually Earth. So Earth is the only scenario where you actually get the moon and the Earth the moon and the sun to appear at the same size from the surface of the planet that they're around, which is just a mind-blowing fact that if you walk away with no data viz knowledge from this stream, you should definitely walk away with that fact, because it's absolutely crazy that only on Earth can we see the moon and the sun appear to be the same size.
So if you're an eclipse enthusiast, do not consider moving to any of them.
Exactly.
In the source.
Mars, let's just look at Mars, because I don't know, maybe one day maybe people will move to Mars. So Mars has 2 moons. As you can see here, pretty underwhelming. The moons on Mars would not even cover the sun. I think they're called Deimos and Phobos. So this is pretty wild. And then I tossed this data set over to Mike, who's also of course data visualization extraordinaire, and he did some really cool explorations. Which again, this link that I'm clicking on is linked in the main notebook here. And so he was kind of looking at the ratios, right? Because if you think about what we're doing here, is we're kind of comparing the ratio of the size that each moon appears to the size that the sun appears. So he started doing some viz around these ratios, kind of looking at, here's the Earth in blue, and then here's ones where the moons are way smaller, here's ones where the moons are way bigger. And then he started kind of exploring in this one. And this is the one where when I saw this, it kind of like made me realize this is the one that I want to make, because I think it makes this phenomenon so obvious. And we're going to kind of, through the course of the stream today, we're going to try to rebuild this and kind of make it even more interesting by using the emojis. But to me, I want us all to like finish the stream by walking away with something that like is kind of like a viral Twitter type thing that you can share, and like really just drives that point home of like, oh my gosh, on Earth we have this like crazy coincidence that the moon and the sun are the same size. And I want us all to like together kind of make this viz that just drives that point home. So that's the goal. That's why we're here. Hopefully you guys can join us for the next 45 minutes or so as we venture down that path to kind of create this. So let me just explain what Mike put together here real quick. For those who can't already tell, Mike made some yellow and gray dots. The gray dots are the size of the moons. The yellow dots are the size of the suns. And as you can see from left to right, we're kind of scanning across how much bigger is the moon versus the sun. And only on Earth do we land in this area where they're like the exact same size. So that's kind of what we're shooting for. I think the next thing I want to do is kind of dive into the data so we can start to like build this up and sort of understand what the data set looks like in order to make this. I guess before I do that, Mike, anything I should add to kind of this little preface here?
No, I'll just do a short little recap. Maybe some folks are just joining us. We've got Matt here, who's an Earth enthusiast based on his love of
right.
eclipses.
The best planet I've ever lived on.
He's on a mission, perhaps pun intended, to show folks that only on Earth can you have this perfect eclipse where the where the moon and the sun are the same apparent size. So Matt shared some of his notebooks. The one that he's looking at right now was really just sort of a sketch pad where I was moving through, sort of experimenting with different ideas. This is one reason that I've really enjoyed working in Observable is I can really quickly prototype different ideas. And if you scroll through this, you'll see I have little notes like, oh, I don't really like this layout, or oh, this didn't really work, or there's too much, there's too much noise in this case, or there's too many observations. So this is not a polished notebook for advertising, but just sort of my thinking through the same problem after Matt sent this data set to me.
Great.
So let's turn back to you, Matt, and start building something sort of emerging from both of these prototypes.
Yeah, cool. Thanks, Mike. And I was just scrolling through the chat, and one of the things I just wanted to kind of touch on is on this visualization, which is admittedly like much harder to kind of like tease out what's actually happening than the one we're going to shoot for. That's part of the reason why we're going to shoot for this one, is because it's so much kind of clearer like what you're looking at. But one thing that I should note about this one is if we're plotting the size of the moon versus the size of the sun, you might think that each kind of point is just a point. It's the size of the moon, the size of the sun. But what you can actually see is each one is actually plotted as a rectangle. And the reason for that is because a few people were kind of catching on this in the comments, is that based on the fact that the orbits aren't perfect circles, right? You remember learning in grade school they're elliptical. So that means the size of, like if I'm standing on Earth, the size of the moon slightly changes as it goes around. And similarly, the size of the sun as it appears from us, not the actual size of the sun, but the apparent size of the sun changes as we move around in our elliptical orbit. So what you can see on this little scatter plot is the reason why each of these points have an actual height and width to them is you're actually seeing the various sizes that the sun could take along the x-axis or that the moon could take along the y-axis. So you can see, like, I don't remember which planet-moon combination this is, but this moon changes in size like tremendously, which means that has a very elliptical orbit. And these ones over here, the sun changes size, meaning the planet's orbit is very elliptical. So I can already tell that one's Pluto, just because I know that one's, I guess, elliptical. But yeah, it's pretty cool to kind of see how you can see the size of the sun change. In fact, even just looking at the Earth here, the Earth has kind of a fairly tightly sized sun. So from our perspective, sun doesn't change size very much compared to some of these other planets. So I just wanted to talk about that. That is something that we're totally going to have to address when we look at the data, because these, NASA nerd data sets, they don't just give us circular numbers, they give us these elliptical numbers. So we're going to have to bust out a little bit of trigonometry in order to get there, but hopefully you guys can kind of bear with us as we go.
All right. Yeah, let's go ahead and dive in, Matt. Let's start building. Cool.
So one of the first things we're going to do is we're going to look at this this solar system data set. So again, this is linked in the main notebook. I've gone through and done sort of the main hard work of getting a couple CSV files from JPL's website. And specifically, I mentioned this during the frozen times, but it has information about the orbits, the size of planets, etc. So I won't dwell on it too much. But what's really cool here is you can use the D3 sort of CSV parser and get these cool objects. I probably won't go through them in too much detail for sake of time, but you can see we have planet-moon combinations. Oh yeah, I totally have these names right. So Deimos and Phobos, and then you can see their radius here. I believe this is in like thousands of kilometers. And then yeah, so then we have the data about the moon's orbits. And these are all NASA terminologies. They're called like semi-major axis. The E is for eccentricity. All these wild terms. So again, I don't want to like make this into a science show. This is not what it's meant to be. But we will have to wade through this a little bit. But don't worry, I'll sort of guide us through it. And then there's the data about the orbits of the planets themselves. So very cool. So I've already kind of like read this in. I've done a little bit of transformation where I've done some slicing and dicing to get an actual map. So this is a JavaScript map where each planet is now a key. And then it's kind of like a dictionary. And I can go look up the individual moons that are part of that planet. But the main thing that I want to look at here is figuring out how to do all this size stuff. So of course, the main variable that we're going to be plotting throughout our journey today through the solar system is size. And the size is based on two variables. This should be pretty intuitive. It's the actual size of the planet itself. And then just like, my head moving forward and away from the camera, the distance away from the observer. So those two variables are like the key things. So if I just look, like I'm just gonna do apparent size of like moon in sky, because there's some trigonometry that we're gonna have to do here, and I just want everyone to kind of gain this intuition for what we're doing. Yeah, cool. So you can see on my screen, I just Google image search just to show that none of this is magic. But there's an actual size of the moon that you can measure in kilometers. And then there's a distance away from the moon in kilometers. But what we want is this angular size. So that's the size of this little like triangle here that you can see is coming out of this dude's like eyeballs, I guess. And so that's the thing that sort of makes, two things that are different sizes appear to be the same size. We all know that the sun is enormous compared to the moon, but if they have the same apparent size, then they'll look the same. And that's what we want to take advantage of. And so that's this angular size. So how do we calculate that? I'm not going to go through too much of the trig, but I just want to show that it's like pretty simple. If you guys remember, trigonometry is all about kind of like converting distances along kind of a unit circle and converting it to angles. And so in this case, we have this distance. You could imagine like a circle that's swept all around this observer. And that circle has the radius called distance in this case. But the thing that we want to measure is actually at a right angle. That's the cool thing about circles, is we could take sort of any sort of cut of the moon, and to a good enough approximation, it'll be the same size. The moon probably isn't a perfect sphere, but good enough for jazz. And so we're going to say that we can cut the moon such that it's at a right angle to our distance, and we now have a right triangle where the sort of flat axis here is distance, and the vertical axis here is the size of our moon, and what we want is this angle. So if you remember your sort of trigonometry rules, that's the opposite over adjacent. And so we can actually use tangent to go ahead and calculate that. But there's actually a sort of another shortcut where we can make it even easier to think about, where because this angle is so small, we can actually use sine because of the fact that this angle is so small. So the distance of the hypotenuse versus the distance to the edge of the moon is kind of the same. So what we're actually going to assume is that we're actually measuring the height so that we can use sine. We could try it with tangent too. It's going to be about the same. But in fact, sine is actually a little bit easier and a little bit actually more correct to use. I probably actually misspoke at the beginning, pardon me, because the real distance is not the distance to sort of like the like portion of the moon up front here. The actual distance that we're measuring is the distance to like this midpoint of the moon, and that's actually what sort of corresponds to the hypotenuse. So I maybe butchered that explanation a little bit, but I just wanted to kind of simplify why we can use this fairly simple calculation called compute arc size. And we basically just take what's called the inverse sine of the radius divided by the distance. And we can actually, just to confirm our intuitions, let's just do this real quick. So compute arc size. let's just do something where the distance is, I don't know, 100 and the radius is 5. Okay, cool, it's like 0.05. But what happens if I increase the radius of the thing? We would expect that my angle here would get bigger. So let's just try that and make sure that this angle gets bigger. Okay, cool, it does. And now let's just try increasing the distance. Let's try doubling the distance. So in theory, we would expect if we double the distance that the size of this thing should probably go down by about half. So let's just try that. Cool. All right, so that's good enough. Kind of confirms our intuition that this function is working well. So what we can do then is we can use that to create this new planet's data structure. So I'm going to walk through kind of what this is. It's a data structure where I have one, it's an array that's one object per planet, so Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. You'll notice I just skipped the planets that don't have any moons. And so what's here is we have the orbital information for the planet going around the sun. And then we have, let's just pick Jupiter as an example. We have an array for moons, and each element of the moon array is now, again, it reminds us what planet I'm from, and then it tells us the name of that moon, and then it has the orbital information for that moon, and then it also has these things called d-min, and that's the distance, and that's what we're going to calculate in this function. So let's go ahead and look at that. Oops. So this is like the core logic behind our visualizations. I realize it's, for sake of time, I'm probably going to blow through this because I want to make sure we get to some of the visual magic. But essentially what I'm doing is for each planet, I'm computing the distance to the sun. Now, we have a minimum distance and a maximum distance, just like we talked about. The Earth kind of moves slightly far and away from the sun as it goes around. So we want to make sure we have a min distance and a max distance. Similarly, for each moon has a min and max distance. And then the apparent size of the sun from each planet has an S, and we use S. That's kind of the canonical number for measuring like an arc size in radians, or canonical letter. I don't know why it's S, but that's what people use. So we have our S min and S max. That's the biggest and smallest size that the sun will appear to be. And then we have our S min and S max for each moon for each planet. So now, if we go look through this data, you can see how we've got all this sweet minimum and maximum distance and size of the sun as it looks from Saturn, and for each moon nested in there, we have all this. Now we have everything that we need to kind of do all this visualization magic. So,
Matt, I can't believe you tricked all of your old coworkers to come watch a trigonometry lesson. That was incredible.
Yeah, exactly.
Clarifying some core concepts from our youths.
Okay, yeah, and they're I'm sure going to be very quick to correct anything I say. So please do. You should trust them more than you trust me. Okay, cool. So yeah, let's get back to the emojis here. So as we talked about, we want to kind of recreate this viz that kind of Mike drafted and kind of threw together, and we want to replace it with the emojis. So the first question is like, how do we even like put an emoji on the page? So okay, I actually made a short notebook for this, and this is kind of what we're gonna. Man, it cracks me up every time I look at this. We're gonna be combining these two notebooks. This one and this one to make our hopefully data viz here. And so I kind of just wanted to like talk really quick about how I did this. So what this is it's a little bit of SVG magic. So in SVG world, you can actually you can do what's called like people call it a def or a definition, where within the actual SVG properties, you can define like external resources. Sometimes people use this for patterns or other sort of like images. In this case, what I've done is you can see I've attached our moon and sun emojis. And the reason why I've attached these as images as opposed to using the like emoji Unicode text themselves is because, as you guys could see, I'm on Unix right now, or I'm on Ubuntu, and these emojis are much less cool than these really hilarious Mac ones. So I want to make sure that everyone can experience the utter joy of these Mac emojis. So we've uploaded them as images so that we can use them that way. That way it's kind of operating system agnostic, and we can all enjoy the hilarious images from these Mac emojis. Cool. So what I do is basically just create a little URL here from our images and basically use this function that I found in this other really cool observable notebook by this guy called Luke. And he, there's no shortage of memes on Observable. And so he built this function. I had to modify it a little bit, and I won't get too much into the details of that. But just one of the other joys of working on Observable is just pick up where other people have left off. And so basically we have this little paradigm where we can just append a circle, and then we can transform it with its x, y, and radius. So that's its position and its size. And as you can see, so let's say I want to change the size of the moon here. You know, I could just change it from 200 to 20. That should change that. Cool. Similarly, if I want to change its position, maybe I want to have it perfectly overlap with the sun. So I'll change them so they have the same x coordinate. Now it's going to be behind the sun, so I can just copy pasta this and throw it in front of the sun. And then, yeah, again, this is like literally makes me, I'm going to laugh so much throughout the course of the rest of the stream. But this is what we've done. So this is really cool. So these are the concepts we're going to take in order to kind of modify Mike's viz. So let's go ahead and kind of rebuild Mike's viz, and then we'll go from there. So when I look at Mike's code, he's got a couple different things going on. He's of course rendering all these circles, but the very first thing you can see that he has is he's got this thing called Dodge Data Mirror, which is something that he built above. So we're going to retake that. And so basically it's the output of this function called mirror dodge, which is I guess, something in one of these other notebooks, which we'll look at in a second. But basically what he's putting into it is he's putting in this data set called moon ratios, which is another thing that he made as basically a transformation of my existing data set. So let's just go ahead and start with this. So this is what we're going to do. We want to make this moon ratio. So you can see hopefully what this is it's taking each possible moon and it's calculating the ratio of the moon versus the sun. So I'm going to go ahead and I'm going to kind of throw this into our notebook. So of course it's not going to work right away for a couple of reasons. One is this function isn't there. So I'm going to go ahead and redefine that or re-implement this function. So Mike wrote this cool thing called get closest ratio, which we will explain in a moment what it is. Oh, you got it? Cool.
Oh, we can just import it.
Yeah, good call. And then the other thing that we need the moon's data set. So where is my data? Cool. So I'm going to import from here. Import moons. And again, this is just the same data set that we've been linking to and talking about. Cool.
So as Matt is typing that out, I'm just going to share that this is one of the first times that I'm getting to do some of this pair programming, that now we're actually both editing the same notebook at the same time. We can even edit the same cell at the same time. That is facilitating some collaborative programming that is really fun and really useful.
Yeah. So, okay, so I already see I got an error, and I got an error called moons.map is not a function, and I'm guessing it's because in your notebook you maybe change the moons a little bit. So let's, yeah. Cool. Oh, actually, why don't we just import it from here? Is it
even better?
Yeah. Okay.
We don't even need to do this get closest ratio.
Yeah, well, that's true.
Oh, can't define moons more than once now.
Yeah, here, I'll get rid of mine. Boom. Oh baby. Okay, cool. So now you guys can already see the the really cool phenomenon that we were talking about, where all these other moons. Oh my gosh, these ones, the decimal points are too low; they don't even render. And then you can see that the coolest moon, capital M moon, is the only one that has this perfect ratio of 1. So we're going to go ahead and try to recreate that cool visual in a way that's a little bit more compelling than that table. So let's go to the next thing, which was, we talked about this dodge thing. So let's do this. And yeah, Mike, maybe you can just quickly talk about what is, or I mean, I can talk about it too, but what's going on with this dodge function. In fact, I'll import that other notebook. So it's basically looks like D3 on Observable has made a notebook that kind of showcases this basically B-swarm algorithm.
Yeah, so if we were to just plot the ratio on a single dimension, right, we plot the ratio of all of these different moons, we're going to have a lot of occlusion, we're going to have a lot of points overlapping each other. And you can turn down the opacity, you can do a few other things, but what you often want is to sort of spread those out vertically so that you can see where each one of those underlying points is. And this B-swarm algorithm is not something that I wrote, but I had seen implemented for a B-swarm chart that essentially takes those overlapping pieces and spreads those out vertically so that we can identify where there are lots of overlapping points.
Boom. Yeah, it's a really cool kind of data viz. Oh, what have I done?
Oh, I also brought in a table.
Oh, okay. No problem. I got it. I will do this. And then add select in here. Cool. Okay, we're getting warmer. We have a couple of errors. R failed to consider. We want range. Cool. And what is okay, cool. So you had built an X scale. So yeah. So one of the things in order to kind of place these circles on this x-axis is to actually create some sort of infrastructure so that our visual knows which ratio corresponds to which position on the screen. So we know, Mike put this little table in here where these ratios are 1. There's obviously ratios of 0. There's also ratios of 5. So how do we know where to put those on the screen? So the kind of common D3 paradigm for this is to create what's called a scale. So I'm assuming that's what Mike's little thing called X is. Yep. And what Mike has done, you can see here, is he created an actual log scale. So we'll show that in a second. It's all good. I'm going to redefine some of this stuff in this notebook just because I think it'd be cool if some of this notebook stands alone.
Yeah, absolutely. That's a trade-off that I often face, is how much to re-import from other notebooks versus just copying and pasting over a couple of cells. And I haven't found a rule about when to do that, and just sort of bump into one wall or the other and decide to redefine or to just sort of clean it up a little bit.
Oh my gosh, we forgot to include the star of our show here.
The star, really, Matt?
Nice. I didn't mean to do that.
Sure.
Okay, cool. Now we're cooking. So we have our Dodge data mirror. So let's actually look at this. So yeah, just for folks who are unfamiliar. So what we've done is we've run this function called mirror dodge. We're storing the result in this little structure called Dodge data mirror. Let's look at what it actually is. So, okay, lots of stuff in here. So you can see each item, there's 177 items, probably, hopefully intuitive that each one maps to one of these 177 moons. So let's look at what else in here. There's X and Y. So each of these X and Y is the position that comes out of that mirror algorithm. And basically, we're just going to steal those X and Ys and we're going to use those to sort of render on the screen. So let's go back to Mike's example here. Which now might get a whole bunch more errors, but let's see.
Copy, paste, get errors. That's sort of what the normal development process looks like, right? Build on some great work of others and see what you can make happen. Okay,
cool. So you've got, you can see there's a radius scale that's not defined. That's the thing that's going to tell us in pixels how big each moon should be.
Oh,
and
you got
voila, we got it. Okay, so now the fun part begins where we want to take what you can see what Mike did is he's got different different circles, and he's got the style of each circle, and he's coloring them yellow or gray based on if it's the moon or the sun. So what we want to do is we want to replace that with this for no other reason than we are just so silly. And so what I'm going to do is I am going to I'm going to paste this function in there again, just because I want this to be a little bit more standalone. And that way, if we want to edit it, we can just do it in one place.
Yeah.
And then
something else, Matt, that is probably new to folks that are maybe JavaScript users but not on Observable is that the ordering of these cells doesn't matter. So you can write them in any order that you want, and that way you can sort of focus where you want to do your work. You can even drag them around. You might have noticed that I just pulled up this radius slider. The math isn't perfect here, but we can sort of experiment with different maximum sizes that we're using.
Yeah, cool. Thanks, Mike. Great. So I've just added images to this notebook, and now I'm going to go ahead and start testing some of the logic from our other little thing here. So what I'm going to first do is I'm going to just add this little bit of infrastructure that adds those, what we call the depths to the. So I'll just add a little comment for this. So add SVG depths. And I broke something. Okay, cool. Don't have the sun and moon URL. Makes sense because I forgot to copy paste them.
And have you also uploaded those file attachments to this notebook?
I did actually just do that.
You did.
Yeah.
Planning ahead, Matt.
I know. But I'm getting a different error now. Unexpected token. I guess that means I probably just have like a stupid semicolon typo or something. Are you able to see it? I'm gonna actually switch to. So I'm actually using the fancy new super feature-rich version. Why was I getting unexpected? Oh, okay. I think I know why this. Is this because I can't do? Why was I getting this?
That's interesting.
Maybe it's because we're in this HTML thing. This is good. People are seeing the live. I'll define these outside.
I was just going to suggest that. I'll get rid of those lets. Ooh,
it's this.
Of course.
Okay.
Because we don't have to find the SVG here.
Yeah. Well, let's see. Okay, so maybe let's just talk about this for 2 seconds. So, kind of what we're running into is the way that I guess we can. Wait, let me just explain this bug. So, basically, what we're running into is you can see what I'm doing in this notebook is I define something called the SVG. And then we use that to sort of like append this image information, and we can append the circle to that SVG. Whereas in sort of Mike's demo notebook, he actually kind of just like writes the SVG inline, and he sort of just like subs in these little values. So it's a little bit of a different paradigm. No one is more right or wrong, I guess, than the other. It's just kind of 2 different flows, and right now we're kind of bumping up against the fact that there's 2 different styles. So I don't know, Mike, what do you think? I guess one way we could do it is we could first basically just re-implement this in sort of a more like
a D3
style.
way.
You want to try that, or is there another thing I should think about that could be quicker?
The only thing is like, do you know what that append child is doing with SVG background image? Like, is that just adding another tag that we could put inside the bottom here? Like after
probably, that's my guess. Yeah, it's just doing. Yeah. Yeah.
Like we can just put that def into the SVG. It might be like a little bit complex, but
yeah, let's give it a shot.
So that is. We'd have to change that function a little bit. I think rather than returning a node, we would just want to return the text.
Yeah, how do we do it? I think you can do, isn't there a HTML, something like that we can do, I think.
Yeah, I think the combining approaches is somewhere that I have run into a little bit of friction. Is there's the Observable is really great at rendering this little piece of HTML, and then D3 is really great at creating that HTML structure and then displaying it.
Yeah.
Maybe we should just flip over to D3.
Flip over to the D3 style? Yeah, let's do it. I think we can knock it out in like a couple minutes.
Yeah. So again, sort of recapping here, we've got this this visualization where D3 is calculating the positions of everything, but we're just rendering each one of these circles explicitly. We're saying for each one of these moons, we should show a circle element, or we should show one for the moon and one for the sun. And where Matt and I are running into trouble is some of the logic behind creating the emojis and how to define those background images. So rather than use this observable style approach to render the elements themselves, what Matt is getting cooking on here is using another part of the D3 library to create the visual elements and append them. And then we're basically going to create the whole scene, the whole SVG element, and then Observable will show it. So D3 is doing a little bit more of the explicit DOM manipulation, sort of creating those visual elements, rather than us typing it out in this sort of iterative style where we iterate through our array. And this is actually a really great exercise in comparing two different styles and sort of pieces of syntax. I was previously much more familiar with the D3 approach that you're seeing Matt start to type up here. And it's been sort of fun flipping back and forth and seeing where we see any friction.
Yeah.
And maybe I'll join you, Matt, in this code. So you've got the data. And then I already know that we're gonna need some different attributes for these.
Yep. So yeah, I want to go, just for folks who are a little bit unfamiliar with D3, you're going to witness some really cool live thought process here. So I want to look at a lot of what you have to do when you're kind of working in D3 is it's really important to remember, or just go look. And that's one of the cool things about Observable. I want to go look at actually what this Dodge data mirror thing actually looks like, so that I can remember what all this stuff is called. Okay, cool. So yeah, it's got an X. It's got Y, and inside it, it's got a data dot ratio. Cool. So it's got all this stuff. So yeah, you can already see Mike has put the Y and X, and then let's just throw a 10 in there. Oh, great. And actually, for this, I can call this R because that's what your slider bar is. That's R. Or is it R over 2? You want R over 2? We'll keep it with R. And then, actually we're actually a lot of the way there. So you know what I'm going to do, just for sake of making it look hilarious as soon as possible. I'm going to throw this in. Shoot, did I? We collided with each other.
Matt, do you want to go ahead and switch back to using next?
So yeah, that's right. Cool.
Yeah. So this, of course, a new feature that we're experimenting with that folks can opt into using, where you can see where your collaborators are.
Cool. All right, great. So now we've got this, and looks like these are a little too high. So I don't know why this is, but I'm just going to add.
Oh, I'm way ahead of you. I've got this G up here that I'm translating.
Oh, okay.
So I'm just putting them all in a little box and then shifting that box down because the Y goes both positively and negatively.
Yeah. Okay. That's right. Okay. Cool. Thank you.
And we're just sort of the width and height.
And then so you're just making a G, and then what I'm going to do is I'll talk through what this git transformation thing is. So while you do that, Mike. So basically, what happens here is, in order to render these things, we can't actually manipulate the actual position of the circle itself because we need the position and the image to follow each other and scale along with each other. So we actually are going to do an SVG translation. And so I actually just wrote this little function because an SVG translation is kind of like this weird syntax. So what I actually did is to do, I wrote a little function, transform, and then we're going to put get transformation, and then in here, we're going to put all our stuff. So we're going to put d.x, d.y, and r, and say a prayer. And it didn't work.
Oof.
I wonder if it's because, hold on, let me try this real quick.
Because you've got this x over my scale, you've got this scaling stuff in here that I don't think we need anymore. In your get transform, because we compute the exact position where we want it to show up.
Yeah, no, but this still has to be there, because what this is actually doing is this is actually changing the size, because basically these images are sort of rendered with the assumption that they are like 100 by 100 or something like that. And so this is actually, here, let's actually just go look in the inspector and see what we got.
Well, Matt, I'm just going to pause real quick. I do want to be respectful of folks' time. I do know that we're at the hour. Matt, if you have time, we can stay along and push through this to get to something cool. But in case there are folks signing off, do you want to say a little bit more about how to best get in touch with you, sort of follow up, learn more, follow you somewhere on the internet?
Yeah, sure. Yeah, thanks for joining. And if anyone hops off, I will absolutely share what I come up with in the next couple minutes on Twitter. So if anyone wants to follow me on Twitter, go ahead. It's just my name @MattDzugan. In fact, I'll just add it to right here. So go ahead and follow me. Yeah, and I will absolutely post our extra dank data viz that we make out of these emojis there. But yeah, I've definitely got a little bit more time. I could probably stay on for another like half hour or so if you'll have me.
I mean, I've got nothing better to do.
Okay, great, cool. Well, yeah, if anyone hops off, thanks for joining. Hope you had fun, and sorry we didn't quite get to this. It happens where you're getting to witness us doing some live debugging, but I'm confident we will get there. And yeah, let's just keep going.
This is the fun. This is the live show, folks. This is how you know it's not pre-recorded.
Yeah,
exactly.
Yeah. This is like the encore, right? We've saved our best, high highs for this moment.
So it does look like we are getting the data rendering.
Ooh, your scale stuff I'm unfamiliar with. Like, I'm not totally sure what that scale 015 does.
Yeah, so let's just try. Whoops. Here, let's actually kind of do something that's basically nothing and see what that does. Okay, so it's not spotting anything.
Is it possible, Matt, that because we're not using the images, because we're just drawing circles, that the scaling is being distorted?
It's definitely possible. So here's a good way to test that. Is let's just do stroke is red, and then we can do like a big old stroke width of. Yeah. So, I'm gonna try this just for. You have an unexpected token. Well, I'm gonna comment your thing real quick. No. Here on my side.
It's funny how we are two, data science, data visualization experts, and like it is still a challenge for us to put circles in the right place. That is still a major problem with this.
It's okay.
It has nothing to do with orbitals and
there was a weird Y at the top of the.
Maybe I planted that just to stretch this out a little bit
testing
longer.
my debugging skills.
Yeah, so we could enjoy our time a little longer.
I mean, it just goes to show that, like, it is tricky. It is tricky to go to space, whether you're going in real life or with data. And I, at least, no matter how long I have been doing this stuff, software development and data viz and whatnot, there are always little things.
I know what one problem is I didn't fill it with the actual emoji. So
right. So if you look up right now the circles with the unscaled, if we just translate it, the translate's working, and we still got the circles on there.
Oh, okay.
It's just a question of how you also do that sort of scaling.
Oops. Okay, we're getting somewhere. We're getting somewhere. I see the yellow thing of the sun.
Yeah. So now we need your scale back.
So now it looks like it's just like the little ear piece of the sun. I guess it's one of those little wave. Oh my gosh.
That was.
Yeah, that's why you got to make them real small. Try to throw in just like a 0.1 or something.
Oh.
Okay.
We're getting somewhere. In the wrong place. Yeah.
Okay, so I don't know why. Here, just humor me for a second. Now that we got this, I'm gonna see what happens if I go back to this guy. No.
So you did something funny in your emoji circles notebook where you made the R100 for the circles.
And that's 100% what it is. That's totally
really 100%. You're gonna make number puns.
Yeah, nice.
Your 100 is the 100%. Come on.
Yeah. No, that's totally related. So, okay. So let's do this. I'm gonna try. Okay. Yep, I can see a sun back there. So now we need to do this d.x again. You should see them spread out. Okay, getting somewhere.
Oh boy.
G.y.
Oh,
okay, now we're getting somewhere.
And let me bring that G back in.
Do that.
Yeah.
Oh god.
Oh, boy.
Okay,
so now,
this is some nightmare stuff here.
This is beautiful.
So yeah, what we need to do, I had totally forgotten about that. So let me just summarize that real quick. So, and I had kind of touched on this a second ago, but like this, just disgusting thing that's happening here is it's all based on like, and you could sort of understand if you had to implement this, you need some way to like relate the size of the actual image, the PNG file, which is just in some arbitrary pixel size. You need to relate that to the size of the circle. And so what I did in this notebook is I based it all off of kind of like using 100 as like the kind of like core currency size that you base everything off of. So, switch to some, yeah. Oh yeah, good call. Good. And so now there's probably a little bit that we can do actually where we change, so I'm gonna call this oh no, this wouldn't be, this is still just 100, but we can change this to be still a little bit too big, right?
I see. Are you trying to size them differently based on the ratio?
Well, I just wanted it to look like this. I think I just had a classic diameter radius issue somewhere in the code. So we're just gonna throw that divide by 2 in there and not think about how it's actually there, and we're just gonna move on. Okay, cool. So the next thing what we want to do. Okay, this is really good. Actually, let's make it a little bit. Can we make it a little bit bigger? So I think if I increase the height, initially that won't do anything because we want to reevaluate this this bee swarm thing. So this bee swarm has to have a height associated with it, wouldn't it?
Yes.
Where did that go? Oh yeah, it has your radius. Oh, so that's right. All we need to do is just slide the slider bar.
Slide it.
I'm gonna slide it. See what happens. Yes. Okay. Cool. Okay. We're getting somewhere. Now we gotta add the moves. So just for, I'm just gonna comment this out so you don't get confused.
Yeah, get rid of it. Trash it.
Okay, trash it. This is so fun. Thank you for bearing with us, everyone. I promise we're gonna have an absolute gem when we get done with this. Okay, actually, how about this, Mike? I'll start doing the moons, and maybe you want to throw some sort of space-related background in the space. I mean, you could go with a flat, just a color. For
no, I wanna do something else. I wanna make this more spacey and annoying. Because with all the orbiting, like we've got to get some spinning, right? We've got to get some rotation happening.
Okay, yeah, we do.
To each of these. I know that in here, where we're positioning them, we've got to scale, we've got to translate. Just to test, if I say rotate 90, they all rotate 90 degrees. So all we need to do is start looping around from 0 to 360 to make all of these rotate. Observable has this great variable called now that tells us the date. But it importantly gives us milliseconds. So if we take now over like 1,000 and use this mod operator, if I were as good of a middle school math teacher as Matt, I'd be able to explain better what the mod does. It tells us the remainder when divided by. So presumably, if this circles around, we can make it go a little bit faster. Once it gets to 360, it should start again at 1. So if I just call this rotation, then rather than 90 in here, Matt has chosen to use this sort of spacing. I'm used to template literals. That's okay. I'll maybe write this line later. Rotation. How's that coming through?
Oh, yep, they're spinning, but it's...
Is it really lagged?
Yeah, no, it's slow. I mean, just like multiply it by 2 or something. I think it's funny.
Is the lag actually, is the rotation too slow, or is it just actually like computationally difficult to spin? It shouldn't be that hard to spin this many SVGs or this many circles.
Yeah. I mean, it is spinning the images too, which is maybe a little bit harder to compute. My computer is singing to me, but you know, that's okay.
That's too bad. I was
oh, there you go.
Somewhere.
I wonder
I
wonder if one thing is that, like, are we recreating that entire SVG every time the time is updating here?
Yeah.
So I wonder if that might
be so
doing a lot of work.
We could do a CSS we could do a CSS animation too.
Ooh. That's outside of my pay grade. I got the circles to spin. It's kind of good enough for me.
Matt, could you scroll down a little bit so we can see the code that that Mike added?
Oh yeah, sorry about that.
No
yep.
Worries.
So he basically took this thing where we had we were using it just to do the scale and translate. He added this rotate part, and then he put this rotation variable. Where'd you add that rotation variable?
Just above the chart.
This is the power of observable collaboration. If folks haven't tried out multiplayer editing, it's great. You can get your work done twice as fast by everybody splitting up.
Exactly.
Awesome.
And mostly, splitting up for debugging. That was the helpful part. We got through those bugs in half the time. Okay, so now we've got these suns here. Now we got to add the moons. So just as like a quick hack to make sure we've got it working, I'm just going to add the moons in here to just be like smaller than the sun without paying attention to what the actual size is supposed to be. I just want to like test that we've got it working.
Excellent.
Yep, we got it. Oh, and the moons are spinning too. Okay. Ooh, they look like it looks like some kind of cookies or something. Okay, sweet. So now what we want to do is we want to make sure that each moon is the size that it's supposed to be, which should just be the size this. It should just be this size times 4 divided by, not sure yet, the ratio that's in that data structure. So let's just try 1. That's the good thing about when there's only 2 options, is you can just try both of them. Okay, so I think if I remember correctly, that ratio was like buried in a...
Yeah, it put inside of data, d.data.ratio. Oh no.
Oh god.
I think it's this, that it's huge.
Oh, that's right. There is one huge moon.
Oh, do something like that? What does that look like?
Oh my gosh, it's beautiful. Except it broke. We gotta pass the. What do you call it? We gotta pass the X and Y position. We can't just put 0 because remember this transformation is the whole string.
Yeah,
so that's fine.
I kind of like that. I think that's hilarious. Let's just have like that one big creepy moon at the offset there to the left.
But the problem is I want to make sure we add it on the right hand side. So I can do that real quick because we just do this and then we do 1. This should do it. Oh yeah. Okay,
wow.
Cool. All right, now we're getting somewhere. I hope people are enjoying this, by the way, because this is just absolutely hilarious to me. I feel like, okay, what else can we do? I feel like in reality, let's clip this a little bit bigger than 1. Let's clip it at like 2. Let's see what
I see. So we'll see some big moons. Yeah.
We'll see big. Yeah. Oh my gosh, these faces. Hold on. You know what?
Yeah, this is really some nightmare stuff. Yeah, that right.
This is really definitely nightmare fuel. But it's scientifically educational nightmare fuel.
Yes. Yes. Absolutely.
So I don't know. What do you think we should do? Ooh, I have an idea. So
before we move on, folks, I think folks are wondering, like, can we get a recap of what we're looking at here? Like, which are these moons, and what was that giant moon, and like, where are we in this picture? And can we get a little recap?
Yeah. Let's do that. So okay, yeah. Thank you for bringing us back to Earth, pun intended. Okay, so what we're looking at is what we're exploring. If you kind of zoom into like the middle of this plot here, you can see there's some cases where a moon is smaller than the sun. Then there's some cases where the moon is just huger than the sun. Earth is actually, I'm assuming, and we'll throw a hover over label on here, but I'm assuming that Earth is this one right here, where oh yeah, thanks, Mike.
I can't even edit the code with that going.
Yeah, I'm assuming that Earth is this one, where the moon is like the perfect same size as the sun. And what's actually interesting is you can sort of see here a good on display is the sort of like exponential size differences in space. Because anything on the left-hand side, the moon is actually being rendered in our viz. It's just so small compared to the sun for those other planets. Like, if you remember, we were talking about Jupiter earlier. I think we were talking about like, just imagine like some of these ones where the size of the moon is like orders of magnitude smaller than the sun. Well, when we plot it on this graph, we're not going to see any of that. And so Mike is reading my mind. I'm assuming that's what this is.
Yeah, that's what I'm trying to do.
To add an actual scale, or what you call like an axis, basically, so that we can read what we're looking at here. So if you remember, we're looking at the ratio of the size of the moon to the size of the sun. And so what would be cool is if we could have, and I'll let Mike show this. I actually have it on one of these. Yeah, you can imagine there's like a little, actually, Mike, I might even have the perfect one ready to go. There's a little, you can imagine a little scale like this that shows, like, in this case, the moon is, 0.1 times the size of the sun. In this case, the moon is 10 times the size of the sun. And that's kind of what we're going to try to add. Oh, it's beautiful. Okay, yeah. And in fact, Mike, I'm going to even edit it further. It took me a while, I remember, to figure out this formatting. This formatting business.
What's wrong with my axis? I have a nice axis.
No, I think we can make it slightly cleaner. If you look at the screen I'm sharing, I like this thing with this like 1x, 2x, because the scientific notation is a little leave something
beautiful.
Desired. So how did I do this? I did, to fixed. So I did tix.toFixed.
I'll let you throw that in there.
I'll try, and if it breaks, I might run away and try to fix it later, because working with the tix scares me sometimes.
Yeah.
But
well, as you fix that to zoom back out slightly, and answer this question as a reminder of what we're seeing is just this ratio of the perceived size of the sun and the moon. So we've got this lovely scale under here. So you can see, and I'm sure we can add just a little bit more annotation or some marking.
I'm going to do that right now.
That at 1x, the only place where the ratio of the size of the perceived size of the moon and the perceived size of the apparent size of the moon and the apparent size of the sun is here on Matt's favorite planet, Earth.
Yep, exactly.
In all the places to the left, the sun is always too large. You never have it fully obscured. You can see the ones that are close to the Earth, where the moon sort of becomes close to the size of the sun, but isn't able to fully eclipse it. And those that are to the right side of the Earth, the moon is too large, so you don't have that sort of background glowing effect when you have the perfect eclipse when they are the same apparent size.
Yep.
We are just so special.
We are.
So special. And I'm going to go ahead and click publish to republish this notebook.
Oh, yeah, I forgot to do that.
So if anyone is following along, I'll put this link back in. Matt and I are able to make changes simultaneously, but only Matt and I are seeing these changes until we choose to share them with anyone else.
We choose now. Okay, cool. So I added a little line. You can see my live struggles with getting this to work. And of course, we could make it look fancier later. But what you're seeing here is this line is like representing that perfect sort of confluence of the shapes for sizes. And yeah, I know one of the other questions Anjana asked was what was going on with that big one. So I can address that real quick. So if you check out these other notebooks that we kind of shared, one of them, I'll show you this one. Let's see. One of them where I've got a lot of notebooks. So if I plot everything at the same scale, so what's cool about this is that when I'm at Earth, I can see how big the sun is. Then when I'm on Mars, I see how big the sun is. You can see the sun is shrinking as I move with each planet. As I move further and further away from the sun shrinks. But then when I get to Pluto, I just have this giant thing, and that's true. Basically, Pluto has an admittedly fairly small moon, but it's super close to Pluto, and so it looks so big, and it sort of destroys our scale. And so, in fact, even if I look at this other notebook where you can see them all plotted together, this ginormo one is this one moon of Pluto. So it's actually kind of crazy to imagine. We can follow up on this on Twitter or something. It's like, what would the sky look like with this moon? Because it's got to take up like a considerable portion of the sky. Well, here's actually a perfect example. If you look at this, so this pair right here, this is Earth and the sun. So if you can think of how big our moon is, and it's this big, and if you could compare that to this, like this is a perfect representation of how big the moon would look. I believe this is, I don't know, is it Pluto's moon Charon, or there's a couple other ones. I'm not sure which one this is. But yeah, it would look, I don't know, what is this? Just visually, like what, 30 times bigger than our moon or something? Like that's what it would look like.
I mean, I
So
personally will be here for it. Like, I love the moon. I love looking at it in the
know.
sky. I want to know what it looks like from Pluto. That looks super cool. Might be
I
terrifying.
know, it's
Might
hilarious.
be terrifying. I mean, you know.
I know, it's something about it that big. I don't know if there's a video game reference here, but Zelda Majora's Mask, they have like this giant scary moon with a face like this. Kind of reminds me of that. So what we were doing is when we were plotting these, before we did this little magic that Mike came up with this, what is this called? Is it called a ternary operator?
It is called a ternary operator, just a really concise if-else statement.
Yeah. So that basically allowed us to clip the size at 2, because if we don't do that, this ginormous one is just going to like blow the entire viz out of the water. And in fact, maybe here's a kind of a cool use case of observable. So let's say I wanted to test this is literally how I use observable most of the time, is like, I want to change the viz. I want to clip it at some number, but I don't know what number to use. Like you saw us initially, we used the number 1, and then I was like, let's move it to 2. So I'm just going to make up a little thing here called like clipping size, and I'm going to,
No, that's my fault.
I'm going to allow it to change between 0 and 10. And let's start it at 2, and let's call it clipping size. This is going to give me a little slider bar. And what I want to do is make that value clipping size.
Ooh, you are getting fancy.
Yeah. So hold on, what happened? Oh,
this is me screwing around.
No, you're good.
Yeah, there you go.
So now you can see. Oh my gosh, I don't know what that image is for Earth, but I like it, whatever it is.
It's much too small to read it. I'm going to try and change the radius too.
And Matt, are you?
So yeah, you can see.
That's one of these like new observable inputs. This range function that you're calling there.
Yeah. Yep,
Cool.
That's exactly what I'm using. And it just basically allows me to kind of like debug through this faster, as opposed to just trying 1, trying 2, trying other values. I can just like slide through, and you can. Oh god. Yeah, and you can see you can see how it changes this. Man, I told you I was gonna laugh this whole time. Okay, what's the name?
Oh no, I did something.
No, it's okay. You got unexpected token.
Well, while we're debugging here, which is always part of the
fun.
Ooh.
We could probably wrap up soon.
Yeah, no. Meanwhile, in chat, there are all kinds of philosophical musings going on about the sun and moon and the effect on the tides, and what would this look like for lunar eclipses? We would have to like calculate the shadows cast by the various planets or planet-like objects. There's like so much more we could explore here. Yeah.
I know that's part of why I wanted to be super certain to kind of like spend a little bit of time talking about. I realize it was probably the most boring part of the stream where I just talked about the data, but like I really believe that you could do so much cool stuff with this data set, and like hopefully I did most of the hard work with the trig of kind of like cleaning it up. But yeah, people should go wild with that data set, because there's so much cool stuff you can do. Okay, now I just want to know what this image is.
Just give me one more second, and I'll get there.
So I'm gonna cheat, and it says it's called screenshot, which is can only mean good things.
All right, did I do it?
Oh, nice! I see what it is.
Oh, sweet home.
It's beautiful. I love it. Yeah, that's us right there on the gray line. It's cool. What are those things called? Crochet? That's not crochet. What is that? Cross stitch. Yeah.
I love this.
That's good.
Now, if somebody wants to cross stitch a version of this data viz that includes a little cross stitched mini cross stitch, that would be really impressive.
Wow. Yeah, that's meta. Cool. Well, I think that's probably about all I wanted to like explore. I think this is really cool. So to summarize, we transformed this data. We realized that like different planet or on different planets, the ratio of the size of the sun to the moon is like different, which can mean different things for eclipses. So what we did is we plotted those ratios. Anything on the left side of this diagram, you can see in the emojis here that the moon is just way smaller than the sun in the sky. Anything on the right side of this diagram, the moon is way bigger than the sun. It totally blocks it. And then right here, where we are on Earth, we just have this like wild coincidence where they are perfectly, literally, can be the exact same size. Now, because the elliptical orbits, there are times when the moon is slightly bigger, slightly smaller. But what's just mind blowing is we are the only place in the solar system where it's even possible for them to be the exact same size. So I think we've made this really cool data viz. I'll probably like poke around it a little bit more after the stream, and I'll post something on Twitter. But I'll definitely post this version on Twitter just to kind of commemorate where we left off here, which I think is awesome. And actually, I'll post the GIF. Yeah, exactly.
Yeah.
I'll post the GIF so that we can get this beloved feature included in the commemorative Twitter version. But yeah, that's about all I have. So anything either of you two wanted to add before we kind of wrap it up?
This has just been awesome. Thank you so much for showing us all of this.
Yeah, I can't thank you enough, Matt. This was super interesting. Part trigonometry lesson, part troubleshooting, Twitch live streaming with Anjana, part moon emojis, 100% laughter. So really enjoyed having you. Looking forward to hopefully having you again sometime.
Yeah, absolutely. Thanks, guys.
Yes, thank you so much for joining us. And thank you, everybody in the chat, for making this so much fun and for bearing with our technical difficulties. And we will be back next week with more streamy goodness. So you can subscribe on Meetup to get notifications of our upcoming events and streams. You can follow us on Twitch, of course. And don't forget to go follow Matt on Twitter. Matt Dzugan, right, is the handle?
Yep. Thanks, guys.
Excellent. Thank you so much. And thank you, Mike, for hosting.
Yep. Bye, guys.
My pleasure. See y'all.
Bye, y'all.